Hello and welcome to our video demonstration of sorting algorithms in PLP. The goal of our program is to take in an array of unsorted numbers and sort them using the bubble sort, insertion sort, and our wildcard sort. So as you can see, it will return the number of cycles it took for the programs to successfully sort these unsorted arrays. So now let's start with explaining our first sort, which is called the bubble sort. The bubble sort is a simple sorting algorithm, and what it does is that it will repeatedly go through the array comparing the adjacent numbers and switching their positions if they're not in order. It will pass through the array until there are no more swaps to be made. So for my code, I've used two counters, and my first counter is T0, and it basically counts the number of comparisons made per iteration, and T1 will count the number of iterations or the number of times it loops the entire array. Here is a basic flowchart of my bubble sort, and you will see that there are two loops into this part. The right side is basically my main loop, which will get the numbers and compare, switch if needed. And the left portion of my flowchart will loop back to my main loop, assuming that T1 is still less than A1. So here you will see that I had actually moved the contents of A0 into S0, and the reason why I had done that is so that I could loop increments of 4 to get to the location of the inputs in the array. Right below that you will see my main loop for my bubble sort, and what it will do is it'll increment the counter for the number of comparisons, which actually that should be T0, not T1, and it checks to see if that number exceeds A1. If it doesn't, it'll load word from the array, increment S0 by 4 to get the next word, or rather the next number, and it will load that, and it'll compare and switch if needed. If it does exceed A1, however, it will branch out to the module and repeat the cycle or iteration if needed. So here is my bubble switch module, which is called upon if it notices that the number on the left is actually greater than the number on the right. So once it switches, it'll store the numbers back into the array and set the pointer back to the last location in the array and jumps back to the main loop. And for my bubble end iteration, this will basically loop my main loop. So this was the left portion of my flowchart earlier, and it counts the number of times that I passed the array. The sorting is normally completed after passing through the array in at most A1 minus 1 times, and then it'll jump back to the main loop if necessary. So now let's go on to the insertion sorting. The insertion sorting is intended for sorting smaller arrays. The sorting method checks elements in the array to find the next smaller element against what it has in the front, which should be the smallest element. If it finds a smaller element than what it is in the front, it moves the smaller element in front and pushes the others back, then starts looking all over again. The insertion sort is similar to the bubble sort in regards to checking the neighboring values to see if they need to be swapped. We found this sort a little tricky, and some of the things we ran into were blocks like not being able to move things inside a stack. Some other issues were failing in initial sorts, missing the final element in the array for sorting, but we did manage to get the return of the number of cycles for sorting. Some of the other fixes to our issues were sorting out the loading into the arrays and fixing the loop count so that the algorithm had time to run fully. While this section of code doesn't entirely work as planned, some things that were beneficial to understanding why were that you should not try and modify memory locations, run lots of tests in your code, understanding the difference between LW and SW, and understanding the incrementing process. Now, to add on to this, we were able to modify the insertion code and to get it working, and we were able to run a lot of successful tests. Now, to move on to wildcard sort. For the wildcard sort algorithm, a count-based sort was implemented. A counter will be incremented from 0 to find the smallest values in the array. The counter increases if no match in all the array is found. Once the counter finds a match, that value is moved to the proper position in the array. This sort requires all elements to be tested and moved to exit the loop, even if the elements are moved into the same space they already occupy. We need to set up 3 counters for this sort, one for the iterations, one for the test value, and one to count that all the elements in the array were checked against so it knows to increment the test value. We covered earlier that this algorithm is slowly incrementing to match values, but I wanted to point out that the default position of the array starts at the beginning and through the course of the loop is moved to the next non-sorted value. So technically it's running through every spot in the array in order to sort the next smallest value. Moving the element after a match has been found, we are swapping the matched lowest value for the position it was found in. So in an array of 3, 2, 1, technically after the first run, the result would be correctly sorted into 1, 2, 3. But because the algorithm must check all numbers, it would then swap 2 for itself and 3 for itself and then end. The following is the flowchart for this wildcard sort. Some of the drawbacks we foresee for this sort is that it could take a large amount of cycles to sort large numbers. Also, the counters and setup for this is more bulky than the other sorting options. It would not be great for large sorts. And that would be the end of our presentation.